You see my screen?
Yes.
Okay, so good afternoon. In this talk, I will present our work on a cutting problem arising in the glass manufacturing industry. This is a joint work with Maria Teresa Alonso and Francisco Parreño from the University of Castilla-La Mancha. The problem came from the ROADEF Euro Challenge 2018. As you probably know, the ROADEF, which is the French OR Society, launches applied problem every 2 years. And in 2018, the problem came from Saint-Gobain, a large producer of glass in France and nowadays in all over the world. So as we were working on cutting problems for several years, we thought this was a good opportunity to apply our knowledge of the problem to a more realistic problem from Saint-Gobain. So in order to understand what is the problem and how the cutting problem arises, I will use this short video to show the production of the flat glass. So the raw materials go to the furnace and are melted there at a very high temperature, near 1600 degrees Celsius. So a liquid glass is produced there. So this glass goes on a molten tin bath and is transformed in a flat ribbon, a very high temperature, as you can see the color of the ribbon. Once the ribbon is composed, it goes through a cooling process in this part of the production process. You can see that the color of the ribbon is changing from red to orange and to blue, indicating that it's cooling down. After that, this ribbon goes through a scan here to identify possible defects. And then when it's cooled down, the ribbon is cut into big pieces called jumbos. So these pieces are collected and sent to the cutting process. So our cutting process starts here when the rumbles have been cut. So summarizing, the glass is cut in jumbos of standard size, 6 meters long and more than 3 meters high. They are stacked in the order they are taken and sent to the cutting part, in which these big pieces are cut into small pieces to meet the customer's demands. There is some problem with the production process because some defects may appear in the beans due to the melting process and also to the movement of the jumbos. So there may be some small air bubbles, some cracks, or even some not correctly melted material. These defects may appear in any part of the beans. We drew the position of the defects in the problem we use as the 10 instances. As you can see, they are completely randomly distributed over the beans. So for our cutting problem, we have some beans that have to be used in a given order. They can't be swapped. And they are always horizontal and can't be rotated. For the items, all items have to be cut to meet the demand. No overproduction is allowed. Items can be rotated by 90 degrees, and items sometimes are grouped into small subsets which are ordered. They call that stacks. For instance, here, if you have a stack of 8 pieces, they had to be cut in this particular order. That imposes a partial order in the way the pieces can be cut. Concerning the cutting process, obviously items can't overlap. Items can't contain any defect. Nobody wants a window with a defect on the glass. And cutting through a defect is not allowed. Only guillotine cuts are allowed, and the process is basically a 3-stage cutting process. First cut is always vertical, second is horizontal, and the third is again vertical. And it's possible at the end of the third stage, if we have a glass rectangle, so we can cut it to produce 2 pieces or 1 piece and a waste area. This is called trimming. There is also some technical questions related to the process in which the glass is cut. There is a minimal width between two cuts. There is also a maximal width in vertical and in horizontal. And there is also a minimal size of the waste, 20 by 20. In millimeters, all the data I will put in my presentation are given in millimeters or square millimeters. The objective is to minimize the waste area of the cutting patterns required to meet all the demands. But there is some consideration about the leftovers that sometimes can be reused. In particular, in this problem, the right part of the last vertical cut in the last bin of the solution is reusable, so it's not considered as a waste. And a small example of how it works. How can we obtain this cutting pattern in which the pieces with the same color belong to the same stack and the small red rectangles correspond to the effects? So the first cut produces a waste area and a rectangle, vertical cut. The second cut is a horizontal cut and produces these three parts. The third stage, again, vertical, produces these pieces. And finally, we can trim this rectangle to produce piece 5 and a waste area. As you can see, pieces 3, 4, and 5 are cut in the order given by the stack. So when we consider all the characteristics of the problem, we decided to develop a beam search algorithm for two main reasons. First, because the problem was highly sequenced and constrained. So we considered that methods based on a constructive procedure would be more suitable than other methods of the heuristics based on populations or on local search. And the second reason is that looking at the literature, we saw that beam search algorithms have been highly successful in other related cutting and packing problems. The main elements of our algorithm are a constructive algorithm, some randomizing strategies, and the beam search structure. For the constructive algorithm, it's an iterative procedure in which we add pieces to be cut. So at each step, we had to decide the empty space in the bin to be cut and the piece or pieces to be cut in this empty space. The first decision is very simple. We use a bottom left strategy, basically following the three-stage cutting process. For the piece to be cut, we have to take into account the stacks, so only the first piece remaining to be cut of each stack is considered. And usually we consider just cutting one piece at each time, with two exceptions. If there is a set of identical pieces corresponding to the same or different stacks, we can consider to cut them together, forming a block. The second case is when we are starting a new vertical cut and we are in the bottom level, we can consider to put two pieces instead of just one piece. Apart from that, in all the other cases, we consider just cutting one piece at a time. The candidate pieces are ordered by some criteria, and the criterion depends on the cutting stage. In the first stage, when we are producing a vertical cut, the criterion is maximal width. In the second stage, when we are producing a horizontal cut, the criterion is maximal height. And when we are finishing cutting a strip and there is just a small empty space left, the criterion is maximal area. This is our constructive algorithm, quite simple. And we decided to randomize it in two ways. First, randomizing the criterion to be used. Although I said in the previous slide that there is a most suitable criterion for each cutting stage, we randomize the selection of the criterion. And once the criterion has been chosen, we order the pieces according to this criterion and also randomize the selection of the piece to be cut. In both cases, it's a biased random selection, in the sense that the elements put in the first position on the ordered list have more probability to be chosen than other elements. But there is some randomization here. For the beam search algorithm, because I suppose you know, or probably you know, that this is a tree structure in which at the root node, the solution is empty, and at each step, branching level, some elements are added to the partial solution until at the bottom of the tree, the solutions are complete. This structure is controlled using 3 parameters. Alpha determines the number of children generated from each parent node. Beta determines the number of nodes to be selected for the global evaluation, is called filter width. And gamma determines the number of nodes kept for the next level, is called beam width. So at the beginning, starting from the empty solution, we generate alpha children using the randomized constructive algorithm. Each children consists of adding 1 strip to the current solution. So these children are all of them locally evaluated using a simple criterion, just the percentage occupancy of the strip, and beta of this, the best beta nodes according to this local evaluation go to the global evaluation, obviously eliminating repeated and dominated strips. So instead of using the classical global evaluation for selecting all nodes to be kept, after some tests, we decided to keep 1/3 of the best nodes according to the local evaluation, 1/3 of the nodes coming from the global evaluation, and also 1/3 of the nodes, the best nodes in a look-ahead evaluation consisting just in adding a second strip to the partial solution. Our tests show that this strategy is better than the classical using only the global evaluation. As in other problems, we try to define some improvement moves. It's not easy in this problem, so we only came up with this improvement mode that I will explain. So it is applied only to the last bin in the solution. Suppose this is the last bin, and the gray part to the right is not used and has a length of 934 millimeters. So the used part of the bin is a length of 5,066 millimeters. So we empty this part, we rotate the bin, and we increase the unused part by 1 unit. So we reduce the part to be used to pack the pieces. So we have this, and we apply the beam search algorithm for the pieces we have removed in the reverse order of the stacks. If all these pieces fit into the reduced bin, we have a feasible solution which is better than the previous one. If it's the case, we rotate back to put the pieces in the corresponding order, and if it is possible, we move everything to the left to increase the unused part at the right-hand side. In this case, from having we use 5,066, we obtain a solution with 5,048. So this move produces some slight improvements in some cases. For the computational study, the organizers of the competition provided sets A and B in the first phases, and then the final phase, the competition, was on set B and unknown set of instances called set X. So we decided to use sets A and B as the training set to decide the best strategy for the algorithms, and then sets B and X as in the competition to test the results of the complete algorithm. You can see here that there is some instances that are really large, more than 600 pieces to be cut, requiring more than 20 bins. So there is some really large instances in this test instances. Well, as you can see for the title of the slide, we didn't win the competition. Luc Libralesso and Florian Fontan won the competition with a very efficient algorithm. our algorithm has some at that moment had some problems that we only found after the competition was over. So we corrected our algorithm and we sent it to the organizers, and they were very kind. So they ran our algorithms in the same conditions as in the final phase of the competition. So our results can be compared directly with those reported in the Roade Challenge webpage. Comparing with the best results obtained by Libralesso and Fontan, we can see that taking as a measure the average waste, we can reduce the average waste in 4.3% when running in a short time limit of 180 seconds, and by 3.3% when running on a long running time of 3,600 seconds. And out of the 30 test instances, we obtained better new solutions in 18 and 19 cases. So we can conclude that our algorithm seems to be very competitive for solving the realistic problem proposed by Saint-Gobain. Finally, we studied the effect of the constraints, basically the defects on the bins and the partial order on the stacks. So if we eliminate the defects on the bins, if we consider the bins are perfect, the average waste is decreased by 22%. If we eliminate the order in the stacks, the average waste is reduced in 37%. If we eliminate both constraints, the average waste is reduced by more than half. We can't think of changing the production process of the glass, so we had to accept that the bins will have always defect, but maybe company could consider the possibility of cutting the pieces in a different way, because eliminating stacks, the average weight will be reduced in 1/3. So as conclusions, the bin search we have developed seems to be well adapted to the problem with the particularity we have included, several ways of adding elements to the solution, randomizing the constructive algorithm, several types of global evaluation and improvement move. And as a future work, when we finished this part, we decided, we wonder if it will be possible to design an integrated linear model. Well, the answer to this question will be the third talk of the session given by Fran Parreño. So that's all. Thank you for your attention. And if there are any questions, I will be glad to answer them.
Thank you very much, Ramon. Any questions, comments? José Fernando?
No, just clapping.
Sorry, but I've just clapped.
Okay.
No, there's just a detail that I did not get. That's regarding the size of the waste. I don't understand if a defect is at least 20 millimeters wide.
The minimum waste.
So you have to cut around the defect. That's the idea. So
in this case, for instance, you cut this blue part, this is a waste, and this blue part the dimensions must be greater than 20 by 20.
Because it has a defect, is that?
Because it has a defect. Yeah.
And it does not depend on the position of the defect inside the waste.
So, no. The only condition is the cut can go through the defect.
Okay.
But it can be as near as the defect as necessary.
Thank you.
Okay, Tony?
Yes, Ramon, so this procedure which you used to optimize the last bin, where you reverse the order, did you do it multiple times, or you only do it once, or does it make sense to do it more than once?
If I remember correctly, if not, Frank could correct me. I think we just used the deterministic, the bin search algorithm, no, Fran?
Yes.
So we tried several times to fit the pieces into the reduced bin, not just one.
No.
We used the bin search. As we applied the complete algorithm for this particular bin and this particular set of pieces with the reverse order of the stacks. Yeah.
Okay, so and I also have another question. Did you think of any other ways to modify your solution to modify an existing solution? because the beam search is very constructive, and with the sequence constraints, it makes a lot of sense. But did you try any ways of modification of an existing solution?
Not really, not really. We just think, well, we didn't think of any other way of modifying the solution, only this one. So that's why we put the randomized constructive algorithm to obtain a diversity of strips when branching from a parent node. But that was all. We didn't come up with any other way of modifying the solution. It's so sequenced and so constrained that we didn't find any other way.
Okay, thank you, Ramon. Thank you.
Okay, Maria Antonia.
Thank you. So first of all, thank you very much, Ramon. It was a very nice talk. Unfortunately, no surprise. It was a very nice talk because you always do it. So I would like, I didn't understand well what the order in the stacks means. You have this, why do they have it, and why?
We don't know exactly how things go in Saint-Gobain, but it seems that if there is an order of several pieces, they want to have it in a given order for some technical reason. They don't explain in the explanation of the problem. They say there is some keeping and some technical reasons, and they decide that some pieces have to be cut in a given order, but we don't have the details really.
But does it depend on the area of the piece, or
no,
decreasing?
No. As you can see in the example, this, well, I can, here, there is all time of pieces can be made a stack, as in the example. All these green pieces are a stack, and there are different type of pieces. That's the data they gave us. I can't say anything about the way in which they define the stacks.
Okay, thank you. Thank you.
Okay, no more questions. Then thanks again, Ramon. And the next speaker is Florian Fontan. Florian, can you share your screen? Okay.
Is it okay?
It's okay.
Yeah, perfect.
Okay, so well, first I would like to thank the organizers of the conference for organizing the conference with this situation. So let me introduce myself very quickly. I defended my PhD a bit more than a year ago, and now I'm working in a French company called Artelis, which is doing service in optimization and also developing solvers. Maybe you know Nitro for nonlinear problems. And so today I'm going to talk about heuristic tree search algorithms for packing problems, and it's a work that I'm doing with Luc Libralesso. So first I will say a few words about heuristic tree search, and then I will talk about how it's applied to packing problems, and finally I will talk about the column generation heuristic. So heuristic tree search algorithm, they have been studied since the 70s in the artificial intelligence community, and they are used in operations research. Well, we saw the beam search just before, but they are a bit less studied than local search algorithm or genetic algorithms. So in heuristic tree search algorithm, we can count greedy algorithms, which is the most simple form of heuristic tree search. Also branch and bound, which can sometimes be used as heuristics. Ant-colony optimization, GRASP, which are known in operations research, and then other more specific to the artificial intelligence community, like beam search, anytime column search, depth first iterative deepening search, and a lot of other variants. So a few words about exact tree search, because we are in operations research very familiar with these algorithms. So in this case, the goal is to terminate the exploration of the search tree. And therefore, it's often necessary to do expensive computations in nodes, like computing relaxations, computing column generations, because it will exponentially reduce the number of nodes that we need to explore. Now, if we want to use an exact tree search as a heuristic, then there are three cases. So let's say we have a time limit of 1 hour. If the algorithm terminates before 1 hour, then we have the optimal solution, so it's very good. If the algorithm doesn't terminate after 1 hour, but it would have terminated after 2, 3, or 4 hours, we will still have explored a significant part of the search tree. And with a standard node selection strategy, it's very likely to finish with a very good solution. The problem is in the third case, when the algorithm will have need days or even more to finish. And if we stop it after 1 hour, then we have only explored a very tiny part of the search tree, and we are likely to have a solution which is not very good or even no solution at all. So does that mean that in this case, it's not possible to use tree search algorithm? So the answer is no. But if you want to use tree search algorithm in this case, there are some elements we need to be careful about. So first, we need to find the good compromise between the time that we spend in nodes to compute information and the number of nodes that we'll be able to explore at the end. Then since we won't explore a lot of nodes, the node selection strategy becomes very crucial for the algorithm. And we need to ensure that we will look at the nodes which correspond to the most promising regions of the search tree. Finally, we can also compromise on the exactness of the branching scheme because we don't want to ensure that it necessarily contains an optimal solution. And for example, in the branching scheme that we use for the most complex problems, there are some tricky cases in which we cannot find the optimal solution, but it's not important because in the common cases, we get very good solutions. So we have been studying these tree search algorithms for quite some time now, and our current conclusion is by default, the best scheme to use is the beam search scheme that I'm going to present here, which is slightly different from the one that we saw in the previous talk. So beam search, it's a breadth first search, and the particularity is that we limit the number of nodes that we keep at each level. So first we start with the root node, then we'll expand it. So here we have set a limit of 5. So after the first level, we have 3 nodes. So it's still okay, no problem. But at the next level, then we have 9 nodes. So what we will do is just prune the least interesting ones. So we have a guide function or evaluation function. We use guide. Which tells us how much the node is interesting. So it's the number that you see next to the nodes. So here we will remove the 4 less interesting nodes. So the one with 4, 5, and 6. We have 5 nodes, and we can expand these remaining nodes and get the next level, and we will remove the less interesting ones, etc. To improve this scheme, we can integrate dominances. So consider, for example, a traveling salesman problem. We are at the branching scheme. We add the next city to visit at each level. And we are at the 4th level, and we have these 2 nodes, 1, 2, 3, 4, and 1, 3, 2, 4. The first one with a current length of 10, and the second with 11. So in this case, we can safely prune the second node, because it's dominated by the first one. So that's what we integrate inside the beam search. So let's take our scheme back. So let's say at the first level, no nodes dominate each other. And now we are at the second level. And before pruning the least interesting nodes, we will check dominances. So for example, in this case, we have these 2 nodes which are dominated by other nodes from our current beam. So let's remark that it's not necessarily the least interesting node. There is one which is dominated and has value of 2, and he wouldn't have been pruned with the guide. So once we have removed the dominated nodes, we remove the least interesting one until we respect the maximum width, and we iterate so on. So remove the dominated ones and then the least interesting ones. So our scheme is almost finished. There is still one thing to take care. What is the beam width to choose? If we choose a small beam width, then the algorithm will behave almost like a greedy algorithm. It will be very fast, but we will have a low quality solution. And if the beam width is large, then it will behave like a breadth first search. So it will take much more time, even if we have a better solution. So the elegant way to deal with this is to use an iterative beam search scheme. So we run successive beam search iteration and we increase the beam width at each iteration. So we start with 1, 2, 4, etc. So with this strategy, we get rid of the width parameter, but we introduce a new one, which is the growth rate that we use in this series. And it's not really a problem because any value between 1.25 and 2 is good. And usually in our experiments, we always use 1.5. Two interesting properties of this scheme is that it's anytime, and it can prove the optimality for easy instances in contrast with local search approach, for example. And it's very useful in practice and also very useful to debug the algorithm. So to sum up these parts, if we want to implement this iterative beam search scheme, we need 3 ingredients: the branching scheme, so what is our root node and how do we generate the children, then the dominance rule, and then the guide, which tells us how much a node is interesting. No additional parameters is required. So let's see now how we applied this scheme to packing problems. So first, the branching scheme. Our root node is the empty solution. Then we choose an item-based approach. So at each level, we add 1 item, and we will look at the possible position following the order of removal of the items, and we will choose which item to add. So for example, we have a partial solution here with 3 items. So the next item can be either in the same second level subplate, in a new second level subplate, or in a new first level subplate, or in a new bin. So we will try all combinations for all items, and we will remove the infeasible one. So for example, this one is clearly infeasible. So we won't generate this child. So with this simple scheme, it's natural to integrate most the constraints from the literature. So the orientation, we handle 2 and 3 stage, exact, non-exact, the defects, and also the other constraints from the challenge. And it's also natural to handle most, all the objectives listed here. So knapsack, bin packing, street packing, or the bin packing with leftovers from the challenge. For the dominance rule, we use this approach. So we compare 2 solutions if they contain the same items. And we look at what we call the front. So it's the border of the solution. And if the front of one solution is before the front of the other solution, then it dominates it. So as illustrated here. For the guide, the main idea is to use the weight over the area. And for knapsack, it will be the area over the profit. And we have then some variations. For example, when we divide by the mean item area, then it will favor adding the larger items first. So now we have defined the branching scheme, the dominance rule, and the guide. So we have our whole algorithm, and we can now look at the results. So first, the results for the problems of the challenge. So these were the results of the challenge. So the second team from Michel Vasquez and Mirsad Bouljoubazik, they had 506, and we had 493. Then what we just saw in the previous talk, Parreno, Alonso, and Alvarez-Valdes, they fixed their algorithm and they got 478, so they improved the results. We also fixed a few elements of our algorithm after the challenge. So in our published version, we have a waste of 469. So in this implementation, it was also a heuristic tree search, but not the same dominance rule, and well, not the same symmetry working strategy, and not the same search strategy. Now, with the scheme that I've presented here, we have a waste of 402. So it's a very significant improvement compared to the previous results. For the knapsack problems, we also have some benchmarks. So for 3-stage, there is one data set where where the heuristic tree search is slightly better than the previous approach from the literature, and one data set where it's slightly worse. On 2-stage, there is one data set where it finds the optimal, well, the best known solutions, as did the previous algorithm. And on the larger data set, it improved the results from the previous approach. For bin packing, the results are also rather satisfactory. So compared to these exact approaches for 3-stage and 2-stage without rotation, we are not very far from the solutions where this algorithm run on longer than the 1 minute we give to the heuristic tree search. And for the 2-stage with rotation, it improved the previous approach, the previous heuristic approach from a QI and QI. And to introduce the next part, I will show the result on cutting stock. So when solutions have several times the same patterns, and in this case, the heuristic tree search is not good at all. The gaps are pretty high compared to the other approaches from the literature. So for the next part, so we have the heuristic tree search, which performs poorly on cutting stock problems. And there is also one classical objective that we cannot handle with this approach, which is variable size bin packing. So when there is a decision on which bin to choose, and the thing is, these cases can naturally be handled by column generation approaches. And if we want to implement a column generation approach, then we will need to solve a pricing problem, which is a knapsack problem. And this knapsack problem, we can solve it with a heuristic tree search. So that's why we decided to implement a column generation based heuristic. So I won't have much time for this part, so we'll be very quick. So variable size bin packing, we have item types, bin types, and we need to select bin types to pack all items and minimize the cost of the bin that we have chosen. There is a classical ILP formulation, but it cannot be solved directly in practice because there is an exponential number of variables. But we can still solve the linear relaxation with the column generation procedure. The pricing problem is a knapsack problem that we solve with the heuristic tree search approach. Then we will use heuristic tree search again to convert the linear relaxation into feasible solutions. So it's a tree search in the branching scheme of the Danzig-Wolf formulation, which means we will branch on columns. For more details about these algorithms, there is a wonderful paper by Sadikov, Van der Beek, Pessoa, Tahiri, and Ushoa. And we have our heuristic. So let's look at the results. On variable size bin packing, we, for the 2-stage with rotation and without rotation, we improved the results from the previous approach. For cutting stock now, with the heuristic column generation, the results are also improved for all cases. So for 3-stage and also 2-stage. And it's also interesting to look at what happens on bin packing, because the heuristic column generation is not always better than the heuristic tree search on these problems, but they are not good on the same instances. The heuristic tree search is very good on instances with a lot of items in bins, and the heuristic column generation is very good at the instances with a small number of items in bins. So if we combine them both, run in parallel and take the best one, then it significantly improves the results. And we see that in these 2 cases, we improve the results from the previous approaches from the literature. Okay, so now conclusion. So I've showed two generic approaches to tackle complex packing problems. They are very effective for the complex problems, but still they are competitive on the more fundamental variants. And it's approaches that we already use for industrial projects in the company I'm working now, Artelis. So I hope I've convinced you that heuristic tree search is a very powerful tool for packing problems. It's easy to understand, it's effective, anytime, flexible, and fast to implement. Actually, it's not good only for packing problems, it's also good for other problems such as the one from these papers, which use the exact same beam search scheme that I've presented here. So for the sequential ordering problem and the permutation flowchart, and obtain state-of-the-art results. I'm not sure I have time to talk about this one, so let's just mention that the codes presented, the algorithms presented here is online. So there is a repository for the packing, for the column generation. We implemented a generic package, which is used by the first one, but can also be used to implement other column generation heuristics for other problems. And we also have some generic packages to help the implementation of heuristic tree search algorithms. Okay, so that's all. Thank you for your attention. And if you have any question, I'd be happy to answer.
Thank you very much, Florian. Very nice talk. Very, very good results. Okay.
Thanks.
Time for one question. Julia.
Thank you, and thank you for the talk. As you may know, I've used beam search a few times, and I'm always thrilled to see other people using beam search. My question is, you used a beam width and pruned at each sort of sequential level of the tree, whereas in many implementations, you would use a filter width and then a beam width, so you'd sort of partially prune at one level and then globally evaluate. Did you try that and find that it didn't help, or did you not try it at all?
We didn't try. We tried the simplest approaches, and since it already works very well, I'm not convinced enough that using this filter scheme would improve the results to get the motivation to try the implementation.
Okay, thank you.
Okay. One more question? No? Thank you very much, Florian. Okay. Going to... Now, can you see my screen?
Yes, we can.
Okay, I'm the last speaker of this session. This is a joint work. One moment. This is a joint work done by Ramon Alvarez from the University of Valencia and by myself from the University of Castilla-La Mancha. This work, one second, has been recently published in Omega. And the point of the starting point is, as Ramon said in the first talk, we thought about the possibility of doing an exact method for this problem. We think about the possibility of a model. Okay, we have a lot of constraints, as Ramon said at the beginning, and about the items and about the cutting process, and we try. This is a toy example in order to explain what is for instance, the question that Jose Fernando asked at the beginning was, this is a solution, an optimal solution with the basic, with no minimum weights. This is a solution in which there is a minimum weight between each cut, each guillotine cut. This is a solution in which we have to satisfy the orders. And this is a solution where it's possible that trimming that is composed by doing this cut after this, and in this we can obtain two pieces. Okay, and finally, This is an example with all the constraints, defect, orders, minimum weight, and so on. Well, we start with a basic model. And after that, we can think about how to incorporate all the constraints about this problem. This is a simple model in which, based on Lodi et al. Model for two-dimensional level packing that can be adapted to the three-stage cutting problem, considering that the first stage vertical cuts define the strips, and the second stage horizontal cut define the levels. Then the items in a level can be cut in the third stage. Okay, and Lodi et al. Consider that items are ordered by height, and their model is based on two main ideas. First, there is always an optimal solution in which the first leftmost item in a level is the tallest in the level. And second, the first bottom level packed in a bin or strip is the tallest level in the bin strip. To allow rotation, we can have two pieces. Okay, this is an example. Here we can see that means that the rotated piece 2 goes in the first level, and we have a variable that indicates that the first level in the first is in the first strip, okay, or the first bin. Okay, the easy constraints that we can think about, I think it's not very difficult, is about, for instance, each item has to be cut. These constraints link each level to the bin and the strip in which it's placed. Here we have, if there are some items in a given level, it must have been initialized by an item. This is the height, this is about the width, and the total width used by the strips in a bin to the bin width. Okay, this is, I think this is more or less easy. Well, the adjusting function is not the typical adjusting function in similar problems. That is most of the time minimize the number of bins. But in this problem, the adjusting function seeks to minimize the total width. We understand the total width, this width plus this width, the last width of the bin. Then we can do that in a model with this objective function and including these constraints. This is the bins are ordered, and we define capital R as this, and then we can have, this is our length of the last bin. Okay, in the previous formulation, we cannot control the order of the pieces into levels, and we are not able to include the constraints related to the trimming. Okay, when we can put two pieces in a guillotine cut. Then we use this formulation that is based on the formulation of Puchinger and Rader. This formulation has a complication that we have to define the maximum number of levels, the maximum number of strips, and the maximum number of bins. And we can do that in order, heuristically, in order to compute that numbers. Okay, in this extended formulation, we have, for instance, that we have two indices for R with the pieces rotated. That is indicate that the item 1 rotated is placed in the second level, in the first strip, in the first bin. And we are going to explain how to include the different conditions. For instance, one of them is imposing the minimum weight condition. We have to define a new variables indicating when the height of item I in level L of strip S of bin is equal to the height of the level. When we have that, we can have, if we have the same level or less than the minimum weight. Okay, for that, in this case, we have that the item 5, the item 2, sorry, in the first level is equal to 1 because the height of this level is equal to the height of the item 2. It's the same with the item 1 and with the item 6. Okay. We also have a condition about imposing the minimum cut, the minimum length of the cut. And we can do in a similar way with these variables that indicate when there is a cut. If there is a cut, this cut has to be longer than the height. I have explained in the height, but there are similar conditions for the width of the beam. Well, now the order. How we can include the orders? The order are included with this constraint. If piece P is placed in a given level of a given strip of a given beam, the previous item in the stack must be placed in a beam before, in a strip before, or in the same strip in a previous or in the same level. And the last one of the constraints that we can solve or we can deal with this model is about trimming. Okay. A first type of trimming is which a glass rectangle obtained in a cut is trimmed to obtain the item. For instance, this. Okay. That we had seen before. However, there is another type like this. Okay. In this trim, the last trim can be used in order to obtain that item. Okay. And we can do it including another set of variables, another set of constraints. Okay, with the previous model, we can deal with minimum cuts, minimum weights, the orders, and the trimming. But now we want to solve the problem of the defect. Okay, handling the defect that can appear anywhere in a beam involves preventing cuts from passing over them and ensuring minimal waste area. This cannot be done without controlling the position of each item on a level. Therefore, we need a new element, the section, to the previous element. Okay. Now we have a section in the last lines. We have strips, levels, and now section. What is the definition of a section? The section of a level are defined by vertical free cuts, like this, or this, or this. Okay, creating rectangles from which either exactly an item or two items applying a further trimming, or an item and a weight, or an item and two weights. Then we have sections, an index more in our, for instance, here is in the first section, item 1 is placed in the first section in the first level of the first strip of the first beam. And this is the same for the rotated in the second section. Okay, this is a mistake. Okay, now with this section, we want to control where is the defect. And then for that, we use these binary variables that solve the problem. Okay, I'm going to explain for different cuts. This variable indicates if the defect D is to the right of the strip S in beam B. I mean, for instance, this is the defect number 5. This is the defect number 6, and then that is the defect number 5 is to the right of the strip 1. Then it's 0. Okay. For the defect 6, we have the defect 6 is to the right of this strip. Okay. And with this condition, we can have when occur one thing or other. Okay, I think that this is the key point for the rest of the binary variables dealing with defects. Then we can do the same for the two cuts, for the levels. Okay, now we define a variable that indicates if the defect is above level L of a strip. For instance, in this case, the defect 5 is above the first level of the first strip. For instance, if we have this variable is 0 because the defect 5 is not above this level. Okay, and these new variables has a strong relation with the previous one, with these constraints. Now we can do something similar to the sections. Is if the defect is to the right of the cut defined the section. For instance, defect 5 is to the right of the first section in the second level, and is not to the right of the second section on the second level. Okay, and these variables are also related with the previous, with the both two sets previous that I have previously said. Okay, but we have to control the left hand side, but now we want to control sorry, the right hand side, and now we have to control the left hand side. Then we have something like that in order if the defect is to the right or not to this left hand side defining the item. Okay, because the section is from here, one is from here to here, and the other is from here to here, and this is the cut producing the item, this item. In the same way that I said before, these constraints are related with the previous one. And we need other variables to control something like this. Okay, imagine in this case, this defect is to the right of, not to the right of this cut, but this is inside when we want to recover this item. Then if the item in the set, if the item in section C of level L is the defect is in this section. Okay, for instance, in this case, this defect is no here. Sorry, here the defect 1 is below the item 1 is below this defect. Okay, and we have some relation in order to all these new variables are consistent. Okay, for implementation we use C+ with a time limit of with this time limit in that computer, and in order to provide initial solution we use the meta-heuristic algorithm that Ramon explained before, which was run with a time limit of 180 seconds. Okay, the computational result for the bin search show that with this time limit, high quality solutions are obtained. Okay, as Ramon said before, through the Rhodes competition, the organizers made available 3 sets. They are huge, with a lot of pieces, and in that instances, the items are small related to bins. The solution show on average of 15 items per bin. In order to test different types of instances, we have adapted the original instances with these 3 sets. By doing so, we have obtained by doing doubling, in this case, and tripling the dimensions of the items. Okay, with exactly the same bins. Okay, with this adaptation, we have this is the original ones where there are around 18 to 20 items per bin. This is the result of the first basic model. This is the result of the complete model. Here we have the number of items I don't have said that the number of items goes from 10. There are 3 classes, 10, 20, and 30. In each class, there are 30 instances. And we can see that even the first model, without defect, without trimming, without order, is very difficult. Only problems with 10 items can be solved. Okay, I have to say that this is the number of optimum, the number of optimal solution, the gap, the average length of the width, the improvement made by the model, the total improvement width, and the percentage of improvement. Okay, and this is with the complete model. I think that the complete model is not able to solve 10 problems of 10 items in 1 hour. Okay, but even in this, for this model, there are space. As Manuel said the first day, even in 2-dimensional problem, we can do things. Okay, this is a solution of this set with 20 items. We can see here, here, and here we have a defect. These instances are the adapted instances where we double the dimensions of the bins. This is always the first model, the basic, very basic model, and the complete model. We can see that here we can solve 3 problems of 20 items optimally, but the gap is increased. Okay, the values of the solution are much higher, reflecting the fact that larger items require more bins. But again, these values increase rather slowly through the models, through these 2 models. Although there is clear increase for the complete model. Okay, in this we need 15,000 and 80,000. Okay, in total. Okay, no, in total, no, sorry, on average. This is an example of this set. Here we have around 8 items per bin. And finally, this is the set where we triple the dimensions. And then we have 4 to 6 items. Okay. The number of optimal solutions is slightly greater than in the previous classes, with some 20 and 30 item instances solved to optimally, and the gaps are slightly lower. The values of the solution obviously increase as large items require more bins, but again, these values are not much greater for more complex models, although a significant increase is observed again. The number, total amount, and percentage of improvement of the heuristic solution is similar to that of the previous class, as shown in the last 3 columns. Okay, this is an example with triple dimension. If we zoom, we can see that the problems are for the defect. These small rectangles are the defect. Okay, and it's very difficult to accommodate. Okay, finally, the conclusion and the future work. We start with a basic model, thinking about integral linear models, and we progressively add new conditions to consider the order in the stack, the minimum waste produced by guillotine cuts, orders in the stack, the possibility of dreaming, and finally defects. We propose the first integral linear model capable of working with trimming and defects. The models obtain optimal or near-optimal solution for small problems, taking into account all the constraints of the real problem. The models can also be easily adapted to other related problems, changing the objective function and something more. And all the source and the model are in this GitHub address. Okay. Last, I would like to thank the reviewers of the paper for the comment because improve a lot the paper. Thank you very much for your attention. If you have any question and if we have time, I'm pleased to try answer them. Okay, wow. Questions, comments? Okay, no comments. I think that I don't know, it's time to stop 5 minutes because we have another session in 5 minutes. Okay.
Yeah.
Thank you.
Should we take 10 minutes?
Okay. Thank you. Yeah.
Okay.
Okay.
Thanks, Fran.
We will see you in 10 minutes. Bye.